In this video, I want to introduce the rising edge detector as an example of a finite state machine, and I'll implement it using Moore and Mealy, and then we're going to take a look at a test bench. So in short, what this particular test bench is going to do, or what this particular finite state machine is going to do, is it'll actually look for a rising edge, like like the name suggests. So we're going to have some sort of an external input to the finite state machine, and it'll always detect this particular edge from 0 all the way to 1. And whenever this happens, it'll actually raise a flag, and that flag is going to be a tick. So let's get started. So the implementation is pretty straightforward. So the Moore implementation is the following. So what we do have is we have about 3 states. Okay, here's the state diagram and the ASM chart. You can read either of them. I'll explain it using the state diagram. And in the state diagram, you can see that what I have is I have 3 states. One is called 0, which tells me that the signal has been at 0 for quite some time. And I have also another state called 1. And what this state tells me, if that was 0, that state will tell me you have been at 1 for quite some time. And I have another state, which is the one in the middle. And that one is actually what's most interesting. It tells me there's an edge, and that is a particular edge that is going from 0 all the way to 1. Okay, and if you take a look at the state diagram, it's again straightforward. So if you have been at 0 for quite some time, and level, which is your external input, has increased, basically moved to 1, that means you do have a rising edge because you're moving from 0 to 1. So you're going to go to the edge state, and in here you're going to issue that tick that tells me that you detected a rising edge. And then whether you did stay, whether the level, if the level stayed, basically you move to level 1. If the level didn't stay, you go back to 0. So you only live within this edge state for just a very short period of time, and that's exactly a 1 clock cycle. You're not going to be issuing that tick for more than 1 tick cycle. And again, this is a Moore output, so you're going to see it written inside the state. So let's see how this is actually implemented in Vivado. So I went ahead and I actually wrote the code for it. It's pretty straightforward. You can see that again I have the inputs and outputs. I have clock and reset as input, level is my external input, the one that I'm actually detecting the edge on, and tick is my output. And I'm basically following this particular diagram exactly how it's described. So you can see in here what I have is I have the enumeration here. Instead of S1 as 0 as like we've seen before, I have 3 states. It's 0, edge, and 1. And I have to use EDG instead of EDGE because edge apparently is a reserved word. So I'm going to have to change it like to EDJ or EDG, okay? And then I define the state type, and then here it's the same as we've seen before. I'm just basically figuring out the state register, and you can see here is I split it into the next state logic and the Moore output, and the next state follows exactly what you do see on this particular state diagram. So I'm moving basically if I'm in state 0, what happens if level is asserted or not, if I'm in edge, if I'm in 1, and so forth. And you can see that the output tick is only asserted when the current state is actually in edge. Pretty straightforward. Okay. Again, let's see how would we do this particular implementation on a Mealy implementation. Okay, so the Mealy implementation is slightly different. As you can see, Mealy has one less state. And this is very, very characteristic of a Mealy versus Moore. You're going to see that Mealy, generally speaking, is a little bit less states. Not always, but generally speaking, that's the case. And you can see in here what I have is I have 2 states. One says 0 and the other one is called 1. So 0 tells me that you've been at 0 for quite some time. 1 tells me that you've been at 1 for quite some time. If you're in state 0 and level has been asserted, you can see that the tick gets implemented at this particular point. Basically, you're moving from 0 to 1, and this is when you assert the tick. Pretty straightforward again. You can follow it on this ASM chart if you choose to. It's the same exact thing, but now I have a Mealy output, so it's actually written on the arrow instead of actually on the transition arrow instead of inside the state. So if you take a look at the implementation, you can see that in Vivado, I already went ahead and wrote those codes, and I'm sharing them with you. Same inputs and output, there's no difference whatsoever. Like now I'm just implementing a Mealy version. And you can see in here the state now, I don't have the edge state, I only have a 0 or 1. The signal here, it's pretty much the same code in here. You can see I changed it a little bit here. I used a different style in here. I combined the next state logic and the output logic together in one combinational always basically in one part. This is so that you get to see a different style. And you can see that I'm actually assuming some sort of default values. Tick is 0 unless I change it somewhere in the code, and the next state is 0 unless I change it somewhere in the code. And then again, the code is pretty straightforward. I know that if I am in state 0 and if level is asserted, this is when I'm actually doing the tick, and this is when I'm moving to next state. The rest is pretty straightforward. So this is a straightforward implementation of these two ones. So let's see how they would actually operate. So the way I did it is I basically wrote some sort of a test bench to actually test both of them, because I want to talk about the difference between melee and more in here. So you're going to see that in this particular test bench, what I have is, let me just do that in here. I think we don't need this anymore. So in the test bench, what we have is I decided the local parameter for the clock, which is t, tells me that this time it's 10 nanosecond. And then the outputs and inputs, I just basically took them from the two modules I'm gonna test. And in this test bench, I'm actually testing a rising edge for melee and more together, so we get to see them on the same graph. And here I'm instantiating the modules under test. So for example, for the melee and the more in here, and if you get to see it, the tick for melee is connected to a signal called tick melee, and for the tick, which is the output, for more, it's connected to tick more, and the rest of the signal are connecting one-to-one. That means the clock is connected to clock, reset is connected to reset, and level is connected to level. Okay, and then you can see in here, this is how I'm generating the clock. I'm generating a reset for a short period of time. You can read this on your own. It's pretty straightforward. And you can see in the stimuli, what I did is I played a little bit with the level. I changed it between 1 and 0 for a certain period of time. What's more interesting in when we run the simulation and to get to see what's happening. So I'm going to run the simulation. And I want to show you a couple of tricks in here. So here's the simulation, and I get to see everything here. It's not very clear, so what I will do is I'll actually remove that parameter because it never changed. And also I want to show you that you can click on a scope, okay, and you can click on objects, and what you can see, for example, I'm stopping at the melee. Let me just show you. This is the melee unit under test. You can see that you have the internal signals in here. So if you decided to see the internal signals on the simulation, you can just as simply as, for example, I want to just see what's the current state. I'm just going to take the state register for the melee, and I'm just going to put it right here. Okay, and that's basically the melee state. It doesn't show anything here because I'll have to rerun the test, but I just want to basically say what state I'm currently at. I'll do the same for the more, and I'm just going to basically drag it and put it right here. So what you need to do is you need to run the simulation. Of course, you're going to be asked to save it, and you do need to save it so that these things never change, because these are not default. So you're going to run the simulation. It's going to tell you it has changed. You want to change it, I'll change, and I'll save a default value and whatnot. And you do have to rerun it to get the states internally, but it's fine. All right. Okay, so here's how this looks like. Okay, so you can see now I do have in here that state 0, state 1, state 0, as we've seen before. Again, the one I put over the melee tick is the melee, and the one I put over the more tick is actually the state, okay, or the more. All right, so let's take a look at here. What you see is I'm issuing the clock. This is at 10 nanosecond interval. That's correct. This is 100 megahertz. It's very similar to what's the clock on the FPGA. That's the purpose of the 10. And I'm issuing the reset for a short period of time. And the reset, again, it just puts both machines in state 0. And that's basically it, the melee and the more. Perfect. And then I'm waiting quite some time to actually change the level. And those sometimes, if you can take a look at the, well, let's put it down in here, for example. I will just drag it and put it in here so we get to see the signals, and you can see that what I'm doing is I'm repeating for 3 the negative edge. So I'm waiting for 1 negative edge, 2nd negative edge, and the 3rd negative edge. And then what I decided to do is I wanted to move 2 nanoseconds. So after 25 by 2, it's like you're going to see 27 nanoseconds, and at this point I'm setting the level to 1. Of course, these are not active edge or anything, but here's the first difference between a melee and a more. So melee depends on the input. So the input has changed from 0 to 1, so the output is going to change instantaneously. And yet this is what you can see in here. So the tick melee has changed directly to 1, indicating that I detected a rising edge. Well, it started from X to 1, but we're going to assume that it's a rising edge. Okay, it's a rising edge. However, the more did not, because the more only changed when the state changes. It will detect it, but it will detect it a little bit delayed. So the first difference between a melee and more, in addition to the number of states, is actually that melee is a little bit faster, so its response is faster. Okay, the next active edge comes in. You can see that now melee moved to state number 1. okay, or state named 1 because it doesn't have the edge, as opposed to the more that actually stayed in the edge for for exactly short period of time, which is in exactly 1 clock cycle. For a whole clock cycle, I'm going to see that the tick is actually stabilized for 1 clock cycle. And then I moved it basically down back to 0. You can see that I'm back to state 0, and the state changes happens exactly at the active edge of the clocks, and this is for both of them. Later on, you can see that I basically changed it at some sort of a negative edge of the clock. Because it's a negative edge is actually not my active edge, you can see again the melee instantly actually changed to 1, as opposed to more, it had to wait for the next active edge to actually tell me that. Okay, so the first difference is between melee and more is that melee is a little bit faster, and in this particular application, it might be a little bit more important to detect the rising edge instantaneously. So I'm detecting the rising edge exactly when that happens. However, what I want you to see is the following. So for melee, I do have this here started between 27 nanosecond all the way to 30. So it started for 3 nanosecond. The tick lasted for 3 nanosecond, as opposed to here, it lasted between 75 to 80 nanosecond, which is 5 nanosecond. So the period of time that that tick in the melee machine lasts is actually not constant, okay? And that might be problematic for synchronous circuits because, as you might know, synchronous circuits actually depends on the active edge of the clock. Everything changes at the active edge of the clock. So it might pose its challenges. However, if you take a look at the more, you're going to see its response is a little bit delayed, but it's exactly for 1 clock cycle. So the clock cycle here is actually 10 nanosecond. You can see from 30 to 40. Here it's going to be basically between 80 to 90 and so forth. So you can see that the melee have a variable period of time. The output has a variable amount of time, as opposed to the more, which is very predictable. So melee sometimes can cause glitches. So something to take care of, to keep in mind when you're actually testing them. Take a look at both codes and the test codes and how I wrote them, and of course you can see the states and how I did them right here.